For God's sake, what now?
Who run Bartertown?
Hi there, I promise the Mad Max quote in the title sequence will make sense in a few minutes. Just give me some time, we'll get there. This project here I'm calling my 8008 Supercomputer. So it has a total of 8 8008 CPUs in it. There are 7 over here in the workers, 1 here in the controller. Now one of the workers you may notice it's not running. That's by design, that's how I divided up the current parallel programming that it's doing. So the 8008, why did I choose that? Well, I've been wanting to do this parallel processing project for several years, and I've thought about using an 8086 or an 8080 or an 8085 or even a Z180, but I never really got started on it. And then I was doing some stuff on the 8008, and I thought, why not go back to the very beginning in order to do this parallel processing project? So why not start with what is widely regarded as the world's first 8-bit microprocessor, the one that started them all, and that is the 8008 that's in here. These were designed in the late 60s. I believe they began being marketed in the early 70s, in 72. I'm actually wearing my vintage 1972 shirt because that's actually the year I was born as well. So here we have the 8008 supercomputer. Now, is it fair to call this a supercomputer? Some people could debate that. You know, supercomputers of the 60s and 70s might have had 256 or more CPUs in them. This only has 8. So sure, it doesn't quite meet that standard. Now at the same time, back in 1972, you would have been extremely lucky to have a single 8008. You know, maybe you'd built yourself something like a Mark 8 computer, one 8008. It would have been just fantastically out of your wildest dreams, I think, to have 8 of them working together, sharing memory, solving a problem. So from a hobbyist perspective, I think this qualifies as a supercomputer. Now, what you're seeing play out on this is currently Conway's Game of Life. Now, this is not the Conway's output there. These are just simple, on the LEDs, these are simple counters showing its progress. Conway's, the grid is actually coming out over here. Now, the goal of this project is not necessarily to write the best implementation of Conway's Game of Life. I wrote what I think is a decent assembly language implementation of it, but I'm sure someone who wanted to take some time to sit down and optimize the algorithm could probably get much better performing. Now, the goal of it was to take that algorithm that I developed and go from a single CPU implementation to spreading it across this entire collection of CPUs to show that we can get better performance out of the parallel processing.
Okay, let's see how I architected this out. So here's this guy. I promised a Mad Max reference. So here we have a Master Blaster from Mad Max Beyond Thunderdome. And it's actually 2 guys here. This one up top here is Master. This one down here is Blaster. And together they fight in the Thunderdome. Master is the brains. And Blaster is the brawn. And together they form a combination. Now, I tend to use these 2 whenever I need to do a sort of parallel computing problem where I want to break it into 2 parts, where one of them's kind of a controller and then one of them's a worker. It's a Master Blaster sounds better than controller worker, doesn't it? Together, you know, we could easily assign 1 CPU to Master and 1 CPU to Blaster. But, you know, we want to go more than that. So what we do is we have 7 Blasters and 1 Master. Adds up to 8. Master is still the brains, and Blaster is still the brawn. But now, you know, we've replicated Blaster out. We can take whatever our problem is, we can divide it into up to 7 parts. And Master will control all those parts. Now, Master can still do a little bit of work on his own. He doesn't just have to sit idly by while Blaster's doing all this work. You know, he may still have some tasks to do. And welcome to the Thunderdome. So here's another way of looking at it, a little bit more conventionally. We'll have Master, and then we'll have up to 7 Blasters. Yeah, the way I designed the bus, you could actually have up to 8, so you could have like a 9 CPU system. But we'll go with just 7 Blasters, 1 Master for a total of 8. And I'm going to use kind of a shared memory abstraction between these, so that each Blaster will have some RAM, and Master will be able to go in here and punch instructions through the Blaster. Tell him what to do, wait for him to do it, and then read back the result. So, okay, let's go through the architecture in a little bit of detail. So here we have Master. Master has an 8008 CPU along with its associated clock, and Master has 16 kilobytes of RAM, that's his kind of working space, and 16 kilobytes of ROM, that's his program, that's his pre-programmed instructions. The 8008 CPU is only able to address 16 kilobytes total. Obviously, we've got 32K here. So there is a memory mapper, so we can map these in 4K pages, just a 74 HCT 670, nothing fancy. We can map these in 4K pages into the 16K of memory space. That'll get more important when we talk about how we control Blaster. So we've got a bus here that connects everything. The bus has got your address lines, your data lines, and your read-write strobes. I'm not going to break all that out independently. It's just a shared bus. Also got a UART down here in 8251, the DB25 connector, so we can have our serial connection in from our terminal and be able to talk to this. And we've also got an output buffer down here, drive some light-emitting diodes because it's nice to be able to light things up and see status. Then over here, we have a bunch of input and output buffers that talk to Blaster. Now these ones here that have 8 ports, they can talk to up to 8 blasters. This one here with just 1 port, it's shared between all the blasters. So here we've got a reset signal. We've got a run. This is an input. It will read whether the blaster is running or halted. An interrupt that we can send to blaster. A take signal so that we can take over blaster's RAM. And a request so that we can ask blaster to do things for us. Now here is Blaster. He's a lot simpler. He's still got his 8008 CPU. He's got an independent clock, and he has 16 kilobytes of RAM, but he has no ROM. Because he has no program of his own, he's only going to do what Master tells him to do. So this RAM, we need to share it between Blaster's CPU and Master's CPU. It's not some fancy dual-ported RAM. Two people can't use it at once. It can only be used by one. So what we're going to do is we'll put some buffers on either side of it with an inverter between them so that we can either have this buffer switched on where the green bus goes through into the RAM or this buffer where the yellow bus goes through. And we'll plumb the yellow bus all the way through into Master. When this buffer is active, Master's bus plumbs through, goes into the RAM. When this buffer is active, Blaster's bus goes through the RAM. One or the other, not both. So how do we control which one of these buffers is active? Well, that's going to be this take line here that comes from Master. This is an output port. If Master sets this bit in the output port, we'll turn on this buffer, and Master will get access to that RAM, and Blaster will be shut off from it. Now, he's not going to be able to do anything because Blaster needs to execute instructions. Even if he's idle, he's going down here, even if he's in the loop or something, he's going down here trying to read his next instruction from RAM. So we need to wait until Blaster is halted before we can touch this RAM. So what we do, we plumb the halt signal through. Sometimes I call it halt, sometimes I call it run. They're just inverses of one another, so that we can tell when or not Blaster is running. If Blaster is not running, then we're free to assert take and mess with the memory. Blaster is running, then we better not assert take because we'll screw up the program. Now, if Blaster is halted, we need some way to wake him up, and that's the interrupt. So an interrupt will pop you right out of a halt. And then, of course, we also need to bootstrap the whole thing. So we have a reset up here. And the reset we'll use after we populated the initial RAM to reset Blaster's CPU to a known state. Start executing the RAM. So what we will do is we'll work in a continuous cycle where we bootstrap Blaster, he starts running, he does an iteration, and then Blaster halts. Once he's halted, we can go in via take, we can mess with the RAM, we'll wake him back up with an interrupt. He'll do another iteration, he'll halt again, we can tell over here that he's halted, we'll do a take, we'll mess with his RAM, then we'll wake him back up with an interrupt. He can do another iteration, and then he'll halt, and then, the whole cycle just keeps repeating. That allows us to kind of share this RAM between Master and Blaster, so long as Blaster is actually doing relatively short tasks. Now, if we wanted Blaster to execute a long-running task, then it might be useful to be able to tell Blaster, hey, I'd like to check up on you. Would you please halt so I can look at your memory? And that's what this request output buffer down here is for. I haven't drawn any lines on this because I'm not actually using it yet. I haven't had a need yet because my iterations are relatively short. This would simply be something where you would write a bit out here. Your program would periodically look for that bit and say, okay, I have a request coming in. Let me voluntarily halt. Even if I have more work to do, I'll voluntarily halt. And then, Master could go in and look at the memory, check up on me, and then wake me back up. Don't need that yet. So this got us to 1 Master and 1 Blaster. Now let's scale out to 8. We'll just add more of them down here, and we'll just hook them up the same way. I'm not going to draw all these lines because the diagram starts to get cluttered, but you can imagine your bus and your chip select. Those can be shared in parallel. You just bring them down and you hook them up to the other blasters. Your reset can also be shared in parallel. We'll just bootstrap them all at the same time. So you run that down, one down, hook to the other blasters. Now on run, interrupt, take, and request, I've drawn 8 ports per each one of these input outputs. So what we can do, 1 bit will return blaster 1 status. Blaster 2, he would connect up to the 2nd bit. Blaster 3 would connect up to the 3rd bit, etc. So reading this port, you could check the run status of all blasters. The interrupt port, similarly, blaster 1 hooks up to the top one. Blaster 2 would hook up to the 2nd one, blaster 3 to the 3rd one, etc. So by writing different values to the interrupt port, we could interrupt any of the blasters, or we could interrupt them all at once. It's up to us. We can interrupt as many as we want. Same thing with take. We can individually take over different ones, or we could take them all over. And the same thing with request. So that's the basics of how it works. There is a lot of details that I've left out of these high-level diagrams. There's a lot of logic in how some of this works, particularly, how the resets work, how the interrupts work.
Okay, let's take a look at master. This is him down here. The way I've designed this, I have master, so he sits flat down on the table with kind of a right angle connection into the backplane, and then the various blasters are standing up next to it. So most important thing would be the CPU. The 8008 is right here. 8008 is a relatively small chip physically, only 18 pins to it, so it sits right there. It requires 14 volts DC, and the way most people do that is with +5 and -9. So we have a 5-volt regulator. This is a little Pololu switching regulator that I like to use, as well as a 9-volt DC to DC converter. This gives us our +5, and this gives us our -9 for our 14 volts for the CPU. There is a jack here on the side that I used when I was testing out master initially, but now he gets the input power from the backplane. So each one of the boards is designed to run off 12 volts. So the 12 volt to come in gets converted to 5, and then gets converted to the -9. So that's our CPU. Over here we've got our DB25 for our serial. Up here is a MAX 202 driver for that serial. We've got a clock and a divider and the UART. So this whole section here is all doing our serial I/O for master. And we've got a little reset circuit in MCP 130, a reset button. We've got the 8 LEDs here. That is the LED output port, as well as this one blue LED, which is the run halt indicator. They're driven by the output buffer there. You'll see some resistor packs around. For example, this one here is the dropping resistor for the LEDs. We've got our ROM here in this ZIF socket, so it's easy to pop it in and out, and our RAM down here. I have relatively big devices in here. I have SF39010. That's what, maybe 128 kilobyte flash memory, and an AS6C, either a 4008 or a 1008. So, again, like 128 kilobyte RAM. We only need 16K of each of those devices. You can actually plug a 62256 into there if you want. And you can plug like a 27256 maybe, the EEPROM into there, 27512. Smaller EEPROMs you can use, but it's really nice to be able to use the parts you have on stock. You've got the crystal here that is the 1 megahertz crystal that goes to the 8008. There's a lot of logic in here that I have covered in my previous 8008 videos, like the various latches and buffers that handle multiplexing the data bus. I'm not going to go into all of that. We have a couple of programmable logic devices that handle I/O addressing and some of the bus signals. I'm not going to go into that. If you want to learn, just how to interact with an 8008 CPU, just watch my previous video where I do dive into all those details on the 8008. And then over here we have the 4 chips that go over to talk to blasters. So, the one that does the interrupts, the takeover signal, the request signal, and gets the run status. So those all are over here. And then we've got the bus connector comes out and goes into blaster. Moving over, it's probably not too easy to see, but you've got the blasters are all plugged into this backplane board. It just runs across the bottom and has a bunch of headers. The backplane, its name is Thunderdome. It continue with the theme that we've been driving here. So let's pull one of these blasters out and take a look at it. It just pulls right out. 3D case here is just to keep these boards aligned so they don't flop back and forth and hit one another. So we'll pull that out, and here we have a blaster. Now he again has his 8008 CPU, again 18 pin, relatively small package right there. He's got his clock for that CPU. Now I designed each one of these to have independent power on it, so we've got another one of the Pololu 5-volt regulators, another one of the minus 9-volt DC-DC converters, and again it pulls 12 volts off of this bus connector to generate that plus 5 and minus 9 for the CPU. You've got another set of LEDs, an output driver for them. Similar to the master board, you know, you've got some logic here, which is kind of discussed in my previous videos. And then you have, you know, a whole bunch of buffers that surround the RAMs. So I've got a 62256 in here now, which is a 30 kilobyte static RAM. We only use 16 kilobytes of it. Blaster is not even capable of using more than 16K. And then surrounding that, we have all kinds of buffers over here. So basically, you saw those in my block diagram. We've got buffers that allow this to be individually switched between the bus or to the CPU. Here we have the bus connector, and we have a set of headers here. I haven't marked them on the board what they do, but one of them is for the request, one of them is for the interrupt, one of them is for the take signal, and one of them is for sensing the run halt signal. And you have to put a jumper on each one to connect the appropriate line into it based on which blaster this is. So if you were to look at, let's take a look at blaster number 3. Number 3 is identical board as number 1, except that the jumpers are in different spots. We've moved the jumpers in 2 places. This makes him board number 3, whereas this guy was board number 1. There's a little bit of a bodge on the back, so it took me a while to get the interrupt stuff working right. I don't know if I'm going to talk about that in the video, but I will at least talk about it in the blog post. Getting the interrupts to work right on this was really complicated, so I had to bodge that up a little bit. This footprint here is just a spare. Now, Blaster does have a 6-pin header here that could, in theory, be used for bit bang serial out. So I was thinking when I designed this thing that I was going to have a lot of trouble getting it working, so I wanted some kind of a way to write serial output. So I put a header on there, and then you could bit bang this port from the 8008 to produce some serial output. I actually never even used that. I managed to get it all working just diagnosing it through the LEDs here. Okay, let's move forward and do a demo. Okay, it's demo time. I've got the supercomputer sitting here. It's not currently powered on, but it is hooked up via serial cable to my Microsoft Propeller VGA terminal. So terminal set for 19.2 kilobaud, same as I've got the UART set to on master down here. So let's go ahead and turn it on. And here we go. You can see this is still based on Jim Luce's monitor, and it's got my own modifications to that, originally for my H8 project, now for the supercomputer project. So if we go into the master menu, let me hit M, we can see there's a bunch of options here. First, I'm going to, well, let's load a program into the blasters. So we will hit L. Now that little pause was it actually writing all of the RAM on the blasters. It wrote them all in parallel, but it wrote its program to all of the RAM. And we can set which program to run. So if I set the ID program, what it is doing now is outputting the ID down here in the LEDs. So you should be able to see this. We've got, 0, 1, 2, 3, 4, 5, and 6. A total of 7 blasters hooked up. We can choose a different program. Let's do free run. And here, it told each of the blasters, let me flip it over, to do a free running counter. So it's just counting from 0 to 255 over and over again. There's actually a loop in there to slow it down, otherwise this would just appear as solid. You wouldn't be able to make out that it's actually moving. Now the blue LEDs light up when it is running. So right now, because like I say, this is a free running counter, it's running all the time. If it gets halted, the blue lights will go out. So let's switch programs again. We will go to program number 2, which is the count and halt program. And what it does is instead of free running, it will display the count once and then halt. So right now it's in a halt waiting for an interrupt. Again, let me tilt this so maybe it's a little more obvious. Now if I push I, it'll send an interrupt. So there we go. You saw a brief blue blip down here. While it woke up, it incremented the counter. It went from 1 to 2, and then it halted again. So we can keep doing that over and over again. I can actually hold it down here, and you can see it, it counting. So this is showing that, it's under master's control, because just like the Conway program will work, it halts in between each iteration. Let's see if I have any more programs. I have one more, which didn't really turn out good before we go to Conway. Let's do Banner. This is actually printing out on here, Scott was here, in 8-bit font. But the problem is these things are a little bit spaced apart, and it's very hard to make out the letters. So if I start to run it here, if you have some imagination, you might see that it is putting across, Scott was here. There was a Scott, was, and here. But like I say, that demo didn't quite work out because it's just not very readable.
Okay, let's talk very quickly about Conway's Game of Life, which is one of my favorite simulations to run on my vintage computers due to the very nice visual effect that it produces. It's played in a grid. This is the Wikipedia page that describes it. You can kind of see how the grid works. The grid cells are either colored or uncolored. The black ones are the colored ones. We'll call those black ones live cells, whereas the empty ones, the white ones, we'll call those dead cells. And it is a cellular automaton. So what you will do is you will execute it in a frame-by-frame basis where you look at the entire grid on a 64 by 24, which is what I usually do. That's 1,500 some odd cells, I think. So you look at an entire grid and you apply some rules to it. If you have a live cell, which is a black dot, with fewer than 2 neighbors, it will die. It will transition to a white cell due to underpopulation. If you have a live cell with 2 or 3 live neighbors, it goes on to the next generation, so it stays alive. And if the live cell has more than 3 live neighbors, it dies as if by overpopulation. Now that handles the live cells, but if you've got a dead cell, which is any of these unlit white ones, and that dead cell has exactly 3 live neighbors, then it will become a live cell as if by reproduction. And those simple rules, when you apply them to a pattern like this, you will get a repeating pattern. So scrolling down, there are several well-known patterns. So first of all, there's some things that are completely stable. Like if you look at this block, each one of these has exactly 3 neighbors. So it just never changes. Same thing with any of these. They just never change. But there's also these things that do change. There's some that will change in place, like the blinker. And there's some that will move like the glider. Now the glider's moving down kind of at an angle. And the glider is the one that I'm going to be simulating using the supercomputer. I'm going to load it up with a glider and let it compute this over and over again, and we'll be able to see the glider move on down through the screen. Okay, how do we map Conway's Game of Life onto the supercomputer? Well, we've got our master and our blasters here, so let's talk about the compute phase. In the compute phase, what I'm going to do is I'm going to divide the Conway's game board into 4 row segments and give each 4 row segment to a blaster. So this one here can do the top 4 rows, he does the next 4, he does the next 4, etc., etc. Now these are not fully independent problems because every time you're evaluating a cell, you're looking at its 8 neighbors. So when this blaster here is evaluating his 4 rows, his top row needs to look at the rows that are typically belong to this guy, and his bottom row kind of overlaps with this guy. So we have to start out by assuming that each blaster has a copy of the board, or at least enough of the board to see its adjacent neighbors. So each one will do this computation on 4 rows at a time. That gives us our parallelism, because that's where the majority of our time is being spent computing, is looking at all of these adjacent 8 values. Now while we're doing this, master is going to be over here outputting the status of the previous run out the serial port. I mean, we might as well have him doing something. He's got a serial port attached, so he'll just report the previous one. I set up a 24 row game board because that's what fits in the terminal. That left 1 blaster left over. And that's why, at the beginning of the video, when you saw one of those blasters was not running his lights, it's this guy. He's just sitting there doing nothing. So anyway, they've all computed. The next step is they will halt and report out. So they all halt. They say, I'm done computing my 4 rows. And master, he goes in and reads all of these boards. So he reads these 4 rows from this guy, this 4 from this one, etc., etc. So he's got a complete picture of what the game board looks like. And then in the next step, he disseminates the complete game board back out, the next version of it. These guys are all still halted, but he gives them the full view so that each of them, they see the full board. Now, the way this is implemented is more efficient than it seems here, because although you have to read each one of these independently, because they're each different sections of data, you can write all 7 of these blasters in parallel. So it's not like I'm wasting time giving each one a copy of the whole board. I have to disseminate the whole board anyway, so just write it to them all at once. Then they all have a copy of the whole board. And then as soon as the whole board has been written, we go back here and we do another compute step where each one does the computes. We do another halt where we read out, and then another update where we cycle back in. And we just repeat that over and over again forever.
Now, let's try our Conway program. So, first I'm going to show you Conway running only on master. And we will hit X, that resets it, and it displays the first frame. Right now we're putting a glider in there. It kind of scrolled off the screen a little bit. 1 row too many. Let's hit this here will run 1 iteration. And you can see some blinking down here. This is master trying to run 1 iteration of Conway. There it did 1 iteration. We can have it do another iteration. It takes what? Maybe about 8 to 10 seconds. Keep going. And that's not using any of the blasters. That's doing it all on master. Now what we can do, we can also do this using blaster. So what I'm going to do is I'm going to change the program to Conway. We'll push another button to reset Conway. These blasters are all ready to go now. And then let me hit 1 iteration. There we go. Much faster. I mean, because we're doing all of those in parallel, we're able to do it in like about 1 second latency. Now, I also have a way to run this just automatic continuous run. So let's show that. I'm going to reset it. I'll load the Conway initial state. Again, this is going to load a glider in. And then I'm going to push this E key for continuous to run. So there it goes. And here we have it actually doing, it's using some escape sequences, so it repaints the screen in place. Rather than scrolling, it just goes back up here to the top. And it's also writing a frame number over there, so we can see it's up to 13, 14 frames. It's going like about a frame per second or so. And you can see our glider slowly start to move across the screen. Down here you can get a good view of what it's actually doing here. You can see the counts. This counter is incremented as each blaster is processing the 64 by 4 space that's assigned to it. And the blue light is lit up when it's running. So the blue light is when it's doing an update, and then the blue light goes out and it does that copy from master back into blaster. And then, it continues to cycle. So it's running pretty quick. And I'll actually put side by side in a few moments. I'll put the one that runs solely on master, the single CPU one versus the 8 CPU one. And we'll be able to see the relative performance difference between the two of them.
Okay, here is a side-by-side comparison. I did this by connecting the supercomputer up to my Windows box and running a terminal program on the Windows box. So on the left, we're looking at a run that was just master alone. And so no blasters at all, just a single CPU scenario on the left. On the right, we have master plus the 6 blasters. So the one I just demoed out there on the main monitor. And, as you can see, the master plus 6 blasters, it runs considerably faster. Just watching this, it feels to me like it's approximately 6 times faster. Now, we would have expected it to be up to 7 times faster because we're going from, 1 CPU to 7 CPUs. But there's probably a little bit of overhead in, doing the copy of the data back and forth, doing the interrupts to trigger, doing the halts. A little bit of overhead. We didn't get quite 700% speed up, but it does feel like it's sped up around 6 times. Just anecdotally, just watching this. So I would say the project here has been a success. I set out to take the same algorithm and, show it in the single CPU configuration, and then come around and show it in the 7 CPU configuration and show that it was faster. So it certainly is faster. Anyhow, I think that's enough for this short little performance comparison here.
Okay, I hope you have enjoyed my video on my 8008 supercomputer. I certainly had fun building it. There are a couple future steps that I might want to take to make it a little bit more supercomputer-like. The first is that I could add numeric coprocessors. So supercomputers of the day would have had numeric coprocessors in them. So there is the AM9511 chip, later licensed as the C8231, that is a simple numeric coprocessor, would do both fixed point integer, multiplies, divides, stuff like that, as well as a host of floating point operations. We could add that. We could add all of that to these blasters here and give each blaster, some decent math capabilities. That interfaces with a simple 8-bit bus, simple port reads and writes. It'd be very easy to add that to these blasters. And with that, I think you would be able to do things like Mandelbrot, fast Fourier transforms, maybe even ray tracing. The other thing I could do is to look at increasing the parallelism. To get to a real supercomputer, maybe we go to 64 CPUs. Now, first I would have to actually get 64 8008 CPUs. I only have 8 of them, so I'd need 56 more. That may not even be possible. But then you'd have to figure out how to extend the architecture. I don't think you can just put 64 of these blasters on a single bus and have it work. No, you would have to go with the star configuration, and maybe you'd have to have 8 groups of 8 blasters. So kind of a 8 times 8. Then you only have 8 of them on the bus at any one time. So that might be what I would pursue. I will have to look into that. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.
Master Blaster runs Bartertown.